Hello guys, welcome back to your channel Gamma Di Gamma. And in this video I wanted to cover another method for solving differential equations, but it is much easier than the other methods. You don't need to do anything special for this, but still it generates some solutions that other methods can't, especially in terms of like special functions. So let's get started. It's called the method of Frobenius. So assume you have a differential equation x squared d second y over dx squared plus 2x dy over dx x squared minus 2 times y equals 0. And notice that this method of ours only works when these coefficients along with the differential operators are some polynomials. It won't work for other cases, and again you want this to be linear. This method of Frobenius works for homogeneous linear differential equation which with the polynomial coefficients. Okay, and it doesn't have to be a second order, we can be a higher order. Homogeneous in the sense that there's a 0. All of this just equals 0. It's linear because you change, like, do a linear combination in place of y, you still get a linear combinations of those individual components. And coefficient polynomials, we have these polynomials multiplied with the y, the different derivatives of y. So how do we solve this is, well, you just assume that the solution can be written as some series. So from n equals 0 to infinity of some coefficient c sub n, x to the n plus s, and where s is some real number. So what we need to do now is find the coefficient Cn and then also solve for s. So let's just plug this into our equation. Notice that the derivative of y with respect to x is just the sum n equals 0 infinity of c sub n, n plus s, x to the n plus s minus 1. So this is just the power rule. And the second derivative of y with respect to x is, well, again, take a derivative of this guy. So you have n plus s minus 1, x to the n plus s minus 2. Okay, we can plug this now, all of these things, into this original equation that we had on top. So we have x squared times the second derivative, which I can substitute from down here, Cn n plus s minus 1, x to the n plus s minus 2, that's the second derivative term, plus 2x and the first derivative term, which is sum from n equals 0 to infinity, Cn n plus s, x to the n plus s minus 1. And then we have an x squared term and a minus 2 term. I can split them up, so I'll write the minus 2 first. Minus 2 times y. Y is just this guy, x to the n plus s. And then for the other guy, I have x squared, sum from n equals 0 infinity, Cn x to the n plus s. All of this equals 0 because it's homogeneous. Okay, I can like club some terms together now. Notice that x squared times this guy will basically cancel out the minus 2 here. X times this minus 1 will go away. And here there's just no integer after n plus s. So we can group all these x to the n plus s terms, because after multiplication this will become x to the n plus s. Same thing here, and is already x to the n plus s. So just grouping those terms together, I now have sum from n equals 0 to infinity of Cn times n plus s times n plus s minus 1, that's this guy, plus 2 times n plus s, that's this guy, minus 2 times x to the n plus s, fine, and we have this guy, so x squared times x to the n plus s is x to the n plus s plus 2. That's a mouthful, but we have precisely that is equal to 0. This is what we get. Okay, now notice that x to the n plus s will trail behind x to the n plus s plus 2 by factor of x squared, because we start with n equals 0, you have x to the s, you have x to the s plus 2 here, so we're always going to trail behind this way. So what you do is the thing that's trailing behind, just expand like some terms of it, and how many terms? Well, by the number it's trailing behind. So this is trailing behind by 2, so we need to expand twice. This is not a general all-inclusive strategy. This is what generally works. If there's like 2 trailing terms, so if there's like a n plus s plus 1, you expand that once because it's trailing behind the highest term by 1, and you expand this twice because it's trailing behind the highest order term by 2. So since it's trailing behind by 2, let's expand by 2. So n equals 0, we have c naught s times s minus 1 plus 2s minus 2, and then c1. This is for n equals 1. So we have s plus 1 times s plus 2 times s plus 1 minus 2. I forgot the x term here. X to the s, and here we have x to the s plus 1. We expanded twice. Now write the others as they are, but now start from n equals 2 because we wrote the first 2 out. So Cn n plus s minus 1 plus 2 times n plus s minus 2 x to the n plus s, and after expanding like twice for the trailing part, we can reindex this guy. So we can reindex this starting from n equals 2 to infinity, and when I do that, this coefficient will now be c sub n minus 2 because there was a c naught here initially. So when you plug in n equals 2, you'll have a c naught, so there's no contradiction there, and just reduce the power by 2 for the same reason. And you notice why I'm doing this? That's because both these sums now start from like n equals 2 and then go to infinity, and both the powers of x in this case are the same, so we can club these last 2 terms. I'm writing the first terms as it is just for some formalism. Sorry, there's an x to the s here, s plus 1, and then just like club all these other terms together. So we have Cn times this entire factor plus c sub n minus 2, and then all of this to the n plus s power. Okay, so notice we have this equation, which is like not a sum or whatever, these 2 guys, and then this entire thing, which is, it seems like a recursive relationship. There's n minus 2 here. So it's time to introduce some terminology. So these guys, which are sort of independent of n, the things we expanded out, these are the indicial equations. So these guys in green here, they're the indicial equation. And this guy in blue, this entire thing, that's the generating equation, because you can generate new coefficients from the one that was before the one that was before it. So 2 before. Okay, and we're going to work with these now, because, well, we want this entire thing to be 0. If a polynomial is 0, each of the powers of x should be 0, or the coefficients associated with the powers. If you want this to be true for every x, we want the coefficients, each of them, to be 0, which means for the first indicial equation, we have c naught times s minus 1 plus 2s minus 2. We want this to be equal to 0. We can assume that c naught is not equal to 0. When we do that, we can solve for this quadratic inside to get two solutions, s equals 1 and s equals negative 2. So we're going to have to break this up into cases for s equals 1 and s equals 2. Okay, case 1, when s equals 1, our solution y of x now can be written as not some cn but some an, for which s will always equal 1. So if you go back here, it's like x to the n plus 1, I think. Yes, x to the n plus 1. This is our first case solution. So since this is an order 2 differential equation, there's going to be two solutions. So this is just the first one. That's why we have two cases. Okay, and now let's just work with this. Since c naught is not equal to this, just translates to a naught not being equal to 0. And now to generate more of these coefficients, we need to use the generating equation. But before that, we need to look at the other indicial equation. So we have, let's see, in terms of a1s, for a, when we have a, which is s equals 1, just substitute s equals 1 here. So we have 2, where c1 now becomes a1. We have 2 times 1, which is 2, plus 2 times, I believe, 2, which is like a 4, minus 2. This just becomes a1 times 4, but this should be equal to 0, which means a1 has to be equal to 0. Just because we use the first indicial equation to get 2 s's, we could have also started with the second indicial equation, got 2 s's, but assumed c1 not equal to 0, in which case c naught would be 0, and you would get the same solutions. So it's kind of futile to use the other indicial equation or preferring the other one over this one. We can choose any. That's why this is kind of cool, because this shows implicitly that this method is going to work, that we're going to get two independent solutions. Anyways, now a naught is not equal to 0, a1 is 0. Let's use this generating equation now. So generating equation, after lots of refactoring and doing the algebra, you can do this by pausing the video if you want, just do it yourself. I'm not going to do it, it's waste of time. It's negative a sub n minus 2 over n squared plus 3n. All I've done here is change the cn's to an an's and taken the s to be 1, because that's when cn is an, right, when s equals 1. So I've done that and then set that equal to 0. Since x can't be 0, the coefficient has to be 0. And rearranging gets you this expression here. That's the generating equation for case 1. Now we know a0 in a1. We can try to do this for a2. For a2 we need a0. And just leave it as it is because we don't know what a0 is. There should be a degree of freedom because we don't know the boundary conditions yet. And n is 2. So this just becomes 4 plus 6 is a 10. For a3, we have now a1 over 3 squared, which is 9 plus 9. But since a1 is 0, this becomes 0. And you notice a pattern going on here. The odd guys will always be 0 because there's always going to be some a1 dependence there. So a5 will be 0. a4 will depend on a0. And so on. This is an infinite series. So sort of expect that to happen. y1 of x, our first solution, sum from n equals 0 to infinity, a sub n x to the n plus 1 can now be written as, let's see, with a0 times x squared for n equals x to the first, sorry, for n equals 0, minus x cubed over 10 and a0 plus a0 x to the fifth over 280, and it's infinite. So you can just pull out an a0, x minus x cubed over 10 plus x to the fifth over 250. It's an infinite series. So that's the first solution. Okay, now let's do this for case 2 when s equals -2. So case 2 is when s equals -2. So now our solution will look like this. y2 of x, sum from n equals 0 to infinity. Now instead of calling it an or cn, call it bn, x to the n minus 2. Now c0 not equal to 0 just translate to b0 not being equal to 0. We still need to check for b1 if b1 is 0 or not. So we have 2 plus 2 minus 1 minus 2. I just plugged in s equals -2 in the second indicial equation for c1, which in this case becomes b1, and b1 should be 0 because the inside guy was never 0. Okay, now let's like get the generating equation. Use this generating equation, substitute s equals -2 and set that equal to 0, this entire thing. So you just get, I'm not doing the algebra, you can do it by pausing the video if you want. P sub n minus 2 divided by n squared minus 3n. Okay. And we have b0 not equal to 0, b1 is equal to 0. We can start for a b2. It was like -b0 over, this guy was 4 minus 6 is a -2, and b3 is b1 over 9 minus 9. But you know, you might see that there's a problem here, but it isn't because we have a 0 over 0 situation. b1 is 0, so it's indeterminate, so we don't know what this value is. It can take any other values. We're just choosing this to be 0 in alignment with what we chose before. Now you might say, you know, we might never have had this problem if we had used the other indicial equation to start with. Well, you can do that and reason that by doing that you get the same conclusion, that this guy will be 0, either as a consequence of it being indeterminate and us choosing a value arbitrarily. But you might say the value that we chose 0 was not that arbitrary because b1 is 0, so it will dominate all the odd terms after that. So don't really bother much about it. You could have chosen any other indicial equation and gotten a 0 without doing this. But if b1 were not 0, then we would have a problem. Then this solution We won't be able to find it using a Frobenius method. We would have to use a Wronskian method, which I'm going to cover after this topic. So okay, B4 is negative B0 over 8. B5 and the others won't have such a problem of indeterminacy as we did before. Okay, so we can write now y2 of x, second independent solution, as sum n equals 0 infinity bn x to the n minus 2, which translates to, taking a b0 out common, 1 over x squared plus 1/2 x to the 0, which is 1, minus x cubed over 8. So notice the difference. It's starting from x to the negative 2 now because of this s equals minus 2 possible value. And these are the two solutions. Y2 is this and y1 is just this. A0 and B0 are subject to the boundary conditions which were not provided to us. So you kind of see this method's nice. It doesn't rely too much on what was given, what was not given, and stuff like that. Another point to note here is that if we would have set this b3 to not equal 0 but some other constant, because it's indeterminate, it has to be some other finite value, then we would have still yielded the same solution. Like the second solution would have been a linear combination with the first one. Like the a-naughts would have gotten added to this one, or some parts of the a-naughts would have, or a-n's would have gotten added. So this is probably a good way of generating independent solutions, by setting one of those guys to 0, and it's pretty much justified. You can try setting b3 not equal to 0, and notice the two solutions. Y2 would have some linear combinations with like these terms like these. So you would not have an independent solution. It would still be a solution. It would be a little more general. But since we want an independent solution, because you can express them, any general solution as a linear combination of two independent solutions, it's just convenient to select b3 as 0 so that you have independence in both of them.